Welcome, everybody. This is the Volatiles session. Rosemary Killen and myself are the co-chairs for this session. I'll be introducing the speakers for the first half, and then Rosemary will take over for the second half. We have 15 minutes for each presentation, so at 13 minutes I will give the speakers a warning, and hopefully you'll finish up quickly enough that we can fit in some questions afterwards. Our first speaker today is going to be Brant Jones, and he's going to talk about the thermal and solar wind-driven water cycle model on airless bodies, the moon as a test case. As soon as it comes up.
Okay. All right. Good morning. Thanks for having me here. My name is Brant Jones. I'm with Georgia Tech. I'm part of the Reveals team. Today I'm going to be talking about a thermal and solar wind-driven cycle. A model that can help explain some of the 2.8 micron absorption features that are currently seen. So our model really stems on two premises. The first one is that solar wind implanted into an oxide-rich mineral will result in this 2.8 micron absorption feature. And this was an idea that was postulated in the late 60s and has been repeatedly demonstrated over and over again in lab-based experiments. And I thought that this was the most recent experiment. However, Jason McLean at Goddard is actually doing stuff on actual Apollo samples. So if you're interested, you should talk to him and stop by his poster. Like I said, the main premise is that proton absorption results in this bound hydroxyl, which gives rise to the 2.8 micron feature. And this is work that was done by Micah Scheibel at the University of Virginia with Raul Barriola. The top one is olivine. The bottom one is middle one is pure. Why is this not working? Yeah, SiO2, and then the bottom one is just a blank where they irradiated SiO2 with helium. And you immediately see that the 2.8 micron feature is there, right? The second thing that you see is the fact that this absorption feature in olivine is really broad. And Starikina kind of postulated this in one of her papers in the mid-2000s, and that is essentially due to the fact that you have a bunch of different cations in olivine, which creates different environments. That translates into slightly different frequencies, which the end result you see is a very broad IR absorption feature, right? So the other thing to point out is this does not produce water, right? As Tony said, we kind of throw this word around loosely, but this really just produces bound hydroxyls, right? And so if you want to then kind of agree with this idea that solar wind is responsible for this 2.9 micron feature, there's a problem because the dominant flux is in the equatorial region, right? So why wouldn't we not see the largest absorption features in the equatorial region? This would kind of imply that there's some removal process of these bound hydroxyls. And the one thing that, the second premise of the model is a process called recombinative desorption. And this is an idea that Tom has been floating around to the community for several years now. And the idea behind that is relatively simple. If you have a surface, a substrate with a bunch of terminal hydroxyls on here, you give it some temperature, they start to wiggle around and react with each other, and eventually will form molecular water and heal that oxygen defect in between those cations, okay? This has been ignored because SiO2 requires a pretty significant temperature. So we're talking about 600 Kelvin before this actually turns on. However, there are other mixed oxides that have a pretty low activation temperature for this to happen. So aluminum Al2O3, this actually starts to happen at about 350 Kelvin, which is now relevant for lunar temperatures, right? The max temperature during the day is about 400 Kelvin. So what we did then for our lunar recipe is to look at the bulk material and then find literature values to plug into this rate into our kinetics model and kind of simulate the process, all right? So also titanium dioxide and magnesium oxide have a significantly low temperature. We're talking now 250 Kelvin before recombinative desorption turns on. And this is what I'll call the coverage independent model, okay? So this, you just need activation energies to plug into this, to describe this. It does not care how much is on the surface. Okay, so this is the overall kinetics model that we used. O.J. Tucker actually has a very similar, well, not similar, another kinetics model, but different, that also kind of explains some of the features that are obscene. So you should check out his poster. It's really nice work. Anyways, so like I said, the main premise here, proton implantation. I don't know why this is not doing anything. Okay. Proton implantation, recombinant desorption, right? That'll form water. Water that can then has several channels of which it can do. It can photodissociate, creating radicals. Some of those radicals will then hit the surface again, reacting with the surface, replenishing the MOH signal. Water can absorb in a cold spot. That's just first order absorption. And then it can also do something called dissociative adsorption, where it'll actually break apart and reform those MH when it hits the surface. Okay, so like I said, this is a kinetics model. You know, from your chemistry classes that you've probably taken before, you build up your differential equations through mass balance, then you ask your computer to solve the concentration as a function of time. Okay, so that's exactly what we did here. This is a result after one lunar day, right? So the vertical axis is latitude, so 0 to 90. I'm assuming that it's symmetrical, so I'm not really looking at, you know, the full spectrum from negative 90 to 90. And then the horizontal axis is lunar time or longitude, however you want to look at that. All right, so blue is 0 parts per million, and as soon as the sun comes on, all right, you're now hitting the surface with hydrogen, creating those MOH bonds, right? Then as the day progresses, the temperature, where are you? Okay. You know, so at lunar noon, now the temperature is the highest point, right? So now you're at 400 Kelvin. This is now relevant for recombinant desorption to happen. That removes some of the OH that you just formed. And then after a while, as the day progresses, the temperature begins to cool off. Now shuts off recombinant desorption. That builds back up the hydroxyl signature, right? So you can kind of think of, you know, this surface rotating. You put your brush on, which is the hydroxyls, leave it off. And that's what you're seeing here. And then the initial or the final values of each day are now the initial values that we plug in, and we just repeat this process over and over and over again. So that's after one day. After 12 lunar days, you start to see this. Notice in the middle here is the diurnal variations that I was talking about. So those are where temperatures are relevant enough for recombinant desorption to happen. And the other thing to see is that you now have this kind of band of OH building up, and that is progressing further and further towards the poles. And this is what it looks like after 1,200 lunar days, right? So you notice that, there's hardly any accumulation in the equatorial region, and you have lots of hydrogen buildup in the polar region. And this, again, is all bound hydroxyls. So this is what we would say that is a 2.8 micron feature. Okay, so if we take a closer look at what's happening here, we have the black line represents the concentration. Whoops. Ignore that. Okay, sorry. Black line represents the concentration as a function of lunar time at various latitudes. So we have 0, 60, and 80. The red line is just a function of temperature. So this is what I'm talking about earlier, where you have sunrise, protons build up. Temperature gets warm enough for recombinant desorption, that drops down, and this builds up again as the temperature cools off. So this is where the diurnal part happens right here. And that happens all the way up to about 78 degrees. After that, the temperatures never get warm enough where recombinant desorption happens, and you just are constantly adding and adding and adding to that area. Okay. So now if we just look at the comparison between observations, and this is from Shuai Li's paper, the first thing you notice is that the shape is relatively similar, and that the trend of the change is also similar. So mornings we have the highest concentrations, noons are the lowest concentration, evenings haven't really got back up to those dawn levels yet. The big difference, however, is the fact, I'll draw your attention to the vertical axis. So they're saying, that they're observing hundreds of parts per million. And not only that, but a pretty significant change on the order of 100 parts per million, too, for a typical diurnal observation. Whereas we, in this model, are basically losing everything, right? So you reach kind of this steady state approximation where everything that you're inputting is now being lost through recombinant desorption. So you never really build up much, and also the diurnal change is significantly less. You'll never have enough solar wind ions to explain 100 part per million change on a day-to-day basis. There just is not enough there. So what that kind of implies that if this is really true, then Lee's observation probably would say that there's actually a layer of water that's desorbing on a day-to-day basis, not chemi-bound hydroxyls. Okay, so the big criticism about that model is the fact that, like I said, it's coverage independent, and there really isn't, pure SiO2 or TiO2 little crystals in the regolith, right? So we have some Apollo samples. So what we did is we did a TPD measurement and actually extracted the energy dependence activation energy for this. And Tom is going to talk about a lot of this in detail later, so I won't get into it, but desorption off the surface can be described by this rate law equation. If you just solve for energy and you have an experimental rate, so this is just the theta is the coverage, right? Fractional coverage is a function of time, then you can get the activation energy as a function of coverage. So this is the TPD of Apollo sample 100084 for water. You have multiple peaks here, which could correspond to different sites coming off. What I'm really going to focus on is this one right here. You notice that water starts to evolve at around 400 Kelvin, slightly below that. So, we fit this and extract the activation energy, and this is what we get. So this is the energy as a function of coverage in terms of kilojoules per mole, and if you want EV, just divide by 100. So the first thing that you should notice is that at large coverage, the activation energy for recombinant desorption is actually fairly low. Whereas at low coverage, the activation energy is fairly high, and that you can just think in terms of the location. If you have two OH molecules that are really far apart from each other, they need a lot of energy to kind of migrate along that surface before they will find each other and react. Whereas if they're really close to each other in the high coverage limit, the activation for that to happen is pretty low. This right here, the sudden drop, is what we believe from what's known as wall contamination issues, and that's we're hitting the substrate up to about 1,000 Kelvin, so you have black body radiation hitting the surface of your chamber walls, which then can absorb water from your chamber walls as well, and that causes contamination in the signal, which is why you see this sudden background or drop in the activation energy. So that's not real. However, this is. So this kind of linear decrease as a function of surface coverage. So then we stick this activation energy in the model, repeat what we just did. This is what you see. Again, the vertical axis is latitude, horizontal axis is the lunar time. And you do not see immediate diurnal change, right? So this is sort of what you would expect, what I said earlier, that the highest concentration of MOH would be in the equatorial region because it's not moving anywhere, it's not going anywhere. However, after you run this, so after 1,200 lunar days, you can kind of see that now the highest concentration is migrating further and further towards the pole, but you still have some residual MOH in the equatorial region. And if we take some slices to look at what's happening here, so this is just the fractional coverage as a function of latitude with each line representing different, thank you, simulation days. So this is what you would expect, right, if the MOH did not leave. However, after a certain amount of time, the surface coverage reaches a point where the activation energy is low enough so that recombinant desorption does happen. And now you reach this steady state scenario where everything that you're putting in is leaving, right? So you're not going to add anything to this. However, the latitudes, the further north you get, are now slightly colder, and there's also less flux hitting the surface at this point. And so it takes a little bit longer to reach that state, and that's why you see this kind of peak migration that's happening right here. This is, again, it's just the same plot, just with different, longer days, so that you can actually see, yeah, there is, no matter how long you run this, there's not going to be any more addition in the equatorial region, and then you'll have this peak migration happening the further along you do the simulation. Okay, so this is a coverage independent model. We talked about this earlier. This is the coverage dependent model, the results that we just got. The same thing, you have this diurnal change, what's happening. The one big difference is the fact that you don't have, you're not removing all of it. There takes a certain amount of time to build up that level right before recombinant desorption happens. And also the total amount changed is significantly less. Now we're talking about 0.05 parts per million on a day-to-day change. This is just a quick comparison between observation and model. This is McCord's data, and then this is the upper and lower limits. There's a bunch of points in here, but you can kind of see that it follows that quite nicely. The poles, remember, like I said, will fill in eventually. You just need to run the simulation longer. I was just limited by the amount of time I was doing this. This is just a video showing it. So I want to say that the hydroxyls are going to be everywhere. There's a very small diurnal change with recombinant desorption, and that it's primarily formed, molecular water is primarily formed through that process, recombinant desorption, and destroyed with photodissociation or dissociative adsorption. And with that, I'd like to say thank you and take questions.
So if you have any questions, please make sure you wait for the microphone because there are people listening online who can't hear you. So are there any questions? All right.
All right, well, I'll be around if something pops up. Please ask. Thanks.
Let's thank our speaker again.